Alright, in this video we're going to talk a little bit about electrophilic aromatic substitution reactions, which from what you've seen already they involve this sort of reaction. Benzene reacting with some electrophilic species, for example bromine, made more electrophilic by the presence of iron 3 bromide, for example, to give, rather than the expected alkene addition product, we get the substitution product. Hence the name of electrophilic, if I can spell this right, electrophilic. Now this is hard to write clearly with. Electrophilic, because we're using an electrophile. Aromatic, duh, from the aromatic ring. And substitution, because of course it's substitution that we're doing versus addition. Now the actual mechanism behind this is essentially electrophile independent. The mechanism is exactly the same each time. So the only thing that you're going to find that's different about all these reactions is the method of generating the electrophile in the first place, and we'll talk a little bit about that. So let's say that I have some electrophilic species here. I'm just going to call it E+ for electrophile. So my benzene, because it's so stable, is not a very good nucleophile. So the rationale behind this is my electrophile has been created here through whatever reagents I have put together, and this electrophile is very, very, very strong. If this is a weak nucleophile, it needs a really strong electrophile to react with, something that's really, really reactive and really wants some electrons. So benzene takes its electrons and grabs that electrophile. And notice that all I did was I showed the electrons coming from the double bond, but I didn't show where. Now it could have been one of these two carbons. So I'm going to show the electrophile on this carbon here. And these two double bonds I'm going to show here because nothing's happened to those. Now just to clarify, benzene has 6 carbons and 6 hydrogens. So at this point in benzene there's a hydrogen on each of these carbons. So therefore I'm going to show those hydrogens on these carbons as well because they haven't gone anywhere. But notice that this double bond has broken, so I'm missing something on this carbon because I had 4 bonds here and now I only have 3. So I have a plus charge here. All right. And what I've done is I have essentially broken or opened up the pi bond system and destroyed my aromaticity. Now the idea is, in order for this reaction to be even vaguely feasible, I have to reform that aromaticity again and get a whole bunch of energy back. So I have to somehow get to this product. This hydrogen stays here, but this hydrogen has to leave. Not only does this hydrogen have to leave, but we have to form a double bond here to get rid of this plus charge. All right. Now usually in generation of the electrophile, some other species would have also been generated. I'll just say this as beef, or I don't know, it might be some sort of base or something like that. Every time you generate an electrophile, there's some other species that you have left over that's going to act as the species here to remove this hydrogen. So this guy comes along, grabs that hydrogen, and because hydrogen can only form one bond, this carbon-hydrogen bond breaks, which takes its electrons and puts them into this bond, giving you your product. So the mechanism for electrophilic aromatic substitution is actually very simple. And I could take any of the reactions that we're going to look at here in a minute and substitute out the electrophile in each case. Oops. So my mechanism here, you could take the electrophile from each of your different reactions and plug them all into the same mechanism, and you'd see the mechanism of substitution is exactly the same. Then the nature of this species would also be different depending on the mechanism, depending on the actual electrophile involved. But once you form the electrophile, this two-step mechanism here is all that happens. So, like we said before, the hardest issue is figuring out exactly how you form the electrophile in each case. So let's just look at a couple of examples. The first one we'll look at is nitration, and that's where we're adding a NO2 group onto a benzene ring, so we get essentially this. So we are making benzene, or we're making nitrobenzene from benzene. Now the species this comes from is nitric acid, but it needs a catalyst to make the reaction go. I know it sounds odd, to make the HNO3 more reactive, or to make it into a more, to give us our strong electrophile, and that's what the sulfuric acid does. So all that happens here is, if I just draw out a basic structure of my two acids here, here is my sulfuric acid, or at least part of the sulfuric acid. I'm drawing out part of it out. I'm only drawing out the bond that's particularly important, that's this OH bond. And then I'm going to draw out the part of the nitric acid that's also important. Because what we have here is a situation where the electron pair on this oxygen from the nitric acid are going to grab this hydrogen from the sulfuric acid, basically telling you that the sulfuric acid is the stronger acid of the two. And so what we end up with, we actually end up with two products, and one of them looks like this, and the other one essentially is the sulfuric acid, but without that extra hydrogen. We have the HSO4 minus ion. Now bear in mind, it's the NO2 group that we are adding in. That NO2 group is clearly going to come from here, and how that's going to form is the oxygen here wants to get rid of that last bond. And if I was to draw this group out in a little bit more detail, if I actually draw my bonds on here, hang on a minute. So we have this, and we have this. I have a negative charge on here, a positive charge on here. I know this looks really odd with two charges next to each other, but I'm just showing you that this guy goes in here and allows that water to leave. And so what we end up with is the extremely electrophilic, this is called the nitronium ion. Alright. So if we go back to our previous slide here, electrophile in this case would be NO2 plus NO2, NO2, and the species here to remove the hydrogen would be the HSO4 minus to regenerate the catalyst. So that is nitration. We can also talk about a very similar reaction that has exactly the same catalyst, and that's something called sulphonation. Alright, where we're going from benzene and we're adding on it's actually called a sulfonic acid group, SO3H. So this is the reaction that we're doing. Okay. And so what that means is then therefore the nucleophile must be something like SO3H plus somewhere, because that's going to be a strong electrophile. So the two reagents here are, there's sulfur trioxide, which is where SO3H is going to come from, and then we have our catalyst, which is the same one as it was before, which is our sulfuric acid. So if I draw out our SO3, it's essentially trigonal planar, and I'm just going to show a lone pair on one of the oxygens, and then I draw out our sulfuric acid again. Remember we said sulfuric acid is a stronger acid than nitric acid, so it's certainly a stronger acid than SO3. So same thing happens. And what we end up with is essentially something that looks like this. So then we have this as well. And just as before, we have HSO4 minus. All right. So the idea is, in this case, remember, sulfur is one of those atoms that can exceed its octet. That's why it's doing this. So the benzene is going to add to this guy. Literally, it's going to go like this, react with the sulfur. The idea being that this oxygen has got too many bonds, so it wants to break one and go like that. Going to give you your SO3H product, or your intermediate anyway, and the HSO4 minus is going to be the species that removes that hydrogen again. So just back to our original slide, the electrophile is the SO3H, so we've got SO3H here, SO3H here, HSO4 minus here. That's nitration and sulfonation, where they both have the same catalyst, which is sulfuric acid. And now we'll look at the last three mechanisms, or the last three reactions, I should say, or really the last three electrophiles, where the catalyst is the same each time. And the first one we will talk about is halogenation. Of course, that means you're adding an halogen, and that's usually bromine, chlorine. You can add in others under certain circumstances, but we're mainly concerned with bromine and chlorine. So the idea is that we make bromobenzene or chlorobenzene. So the first thing that's going to happen is, well, let's just look at the overall reaction, all right, because we need to know what our catalyst is, because we were looking at it before. So we're adding our Br2, and we get this substitution reaction, but only in the presence of a catalyst such as FeBr3. Now you'll see several different types of catalysts to do this. You'll see FeBr3 works fine if you have bromine. FeCl3 works fine if you have chlorine, and so does AlCl3. So these three essentially have the same function. So the catalyst here is our FeBr3. So the question we have to figure out is, what exactly is happening to make that bromine more electrophilic to make the benzene react with it? Well, let me just draw out bromine here. It's got all these electron pairs around the place. And if you know anything about iron bromide, or really any salt of iron, or really any transition metal, is that these guys can act as Lewis acids. Now, if you remember what a Lewis acid is, it's something that can accept electrons. If you look up the electron configuration, or you figure it out for iron, you'll see it has empty d orbitals. I think it has 5 or 6 d electrons. It has 6 d electrons in its 3D shell, meaning there is plenty of room for more electrons to go. And that's one thing about all transition metals. They can act that way. So what the bromine does is takes its electrons and grabs onto that ion. And so what we actually form is something that looks kind of like this. And we have this here. Now, when we look at formal charges here, anytime you take electrons and add them into something that already has 0 charge, it's going to have a negative formal charge after you're done. And the bromine, if you figure all this out, with its 1 extra bond and still its 2 lone pairs, it has a positive formal charge. Okay. So the idea is then, at this point, that this thing is the electrophile. The benzene comes out, grabs that bromine, and the idea is that it grabs this bromine because this bond wants to break and go onto here to give that bromine its 1 bond back. And what we end up with is the bromine added onto the ring, and we get this FeBr4 minus complex, which acts as the species to remove the hydrogen from here. So in this reaction we'd have the FeBr3 as the catalyst. We'd have a Br here, FeBr4 minus here. Then when it grabs the hydrogen, it breaks back down to HBr and FeBr3. Remember, this is a catalyst, so it has to reform. So this FeBr3 works this way for this reaction. It works the same way for the other two reactions as well, and those are called Friedel-Crafts, Alkylation, and acylation. Alkylation means you're adding on an alkyl group. Acylation means you're adding on an acyl group or ketone. Let's just look at the electrophiles for each. All right. Let's say we wanted to add something like 1-chloropropane onto a benzene ring. The only way we can do that is if we have the catalyst there as well. So we have our catalyst just as we had it for the bromination or halogenation reaction, and exactly the same thing happens here. We have our halogen with all its electrons, and what it does is we essentially get something that looks like this. Same thing as before, negative formal charge here, positive formal charge here. Now the only thing we have to be concerned about with Friedel-Crafts alkylation, because that's what this is that what happens next is this bond breaks, and this is where we have to be careful. It breaks because it wants to give the chlorine that one bond back. So we get two species. We get this, and we get FeCl4 minus, which is going to be the species that grabs our hydrogen from our ring to reform our aromaticity. The thing we have to be careful about is this one, because what sort of species is this? It's something that we've seen before, and this is a carbocation. Carbocation. Now, why do we have to be careful about this? Well, the reason we have to be careful is because we have to remember exactly what carbocations do if they can. And this one is going to do exactly what it did the last time we saw it, and that is, if a carbocation can rearrange to something more stable, then it will, which is what this one will do. It'll undergo a hydride shift and take us from a primary carbocation to a secondary one. And so that's why, and so that's the benzene ring that goes and attacks that carbon. So you have to be careful sometimes with this alkylation reaction, simply because of the fact that if I draw out this, so I have my 1-chloropropane, my FeCl3, I have to be careful of the fact that I don't necessarily form the product that I would expect. Because unless I go through the mechanism, I don't know that's necessarily going to rearrange to form this product. That would be the product. That's my substitution reaction, formed from this intermediate. So once again, going back to our front page again, this would be our rearranged carbocation. That would be our isopropyl here, and the FeCl4 minus would be here. Alright, let's look at acylation now. This one is a little less involved because there's no rearrangement issues. Alright, so it's not a good start. So what we start with in this case is not an alkyl halide, as we started with last time, alkyl halide here. We actually start with an acid chloride, because we have to have some way of adding in this carbonyl group into our product. We have exactly the same catalyst, And so what do you think is going to happen? Well, it's exactly the same thing as happened before. FeCl3 acts as a Lewis acid. We put this here. We get this here. We get our intermediate species here. Once again, this bond breaks. Now, what we get in this case, though, we get something called an acylium ion. Doesn't mean it's silly, it's just the name of the structure. That's not funny. And so what it actually looks like is, it looks broadly like this. So we've broken that bond. So we broke this bond here, and so that carbon now only has 3 bonds to it. So it has a plus charge on it. You might say it doesn't look very happy. But the one thing that we have here is we have an oxygen next to it that has a pair of electrons that they can funnel into here, into this double bond, make it a triple bond. And so what we end up with is this. That's a triple bond right there with a plus charge on the oxygen. The important thing is here we have resonance stabilization. So the acylium ion, although it doesn't look stable, it's actually more stable than you would expect because of the fact there's resonance stabilization here. The nice thing about this acylation reaction is that there is no rearrangement issues to worry about because we don't have our typical carbocation that we had for the alkylation. So in some reactions you need to actually use this. Oh, it didn't look very good. You need to use this to avoid any rearrangement problems. Anyway, so when we go back to our first page again, our acylium ion would be our electrophile, so the ketone would be here and here, and then the FeCl4 minus would be the species here. So I'm hoping what you've seen over these few slides is the fact that each of these 5 reactions is essentially the same. The only thing that's even vaguely different is the mechanism by which the electrophile forms, and really it's only 2 separate mechanisms. There's the mechanism where sulfuric acid is the catalyst, and then the mechanism where the FeBr or FeCl3 is the catalyst. And there you go.